Hello students, so today we'll discuss about a permanent magnetic nanocrystalline materials, as you can see. Now we'll first start with considering there is a mixture called a two-phase mixture of a hard magnetic phase and a soft magnetic phase. Hard as well as soft magnetic phases. Now by hard we mean that there is a the coercivity is high. That means if you plot the image plot, the hard will give a shorter and a wider hysteresis slope, but as compared, but the soft one will give even narrower but thinner, longer but thinner hysteresis slope. This is for the soft, and this one stands for the hard magnet. Now we are dealing with the fact that we have now mixed these two materials. Now what has been found is that uh, the remittance magnetization, that means this one, the one that retains from 0 it goes, and when it is brought back to 0, this is your MR. This value is greater than the isotropic value of 0.5 ms. Now, usually, reminiscence value is considered to be half of the saturation value. Now, let's not be the case. That means if this is the saturation value, it is assumed that this MR will be half of this MS normally. But what has been found that on mixing a hard phase and a soft phase, it is more than half. Now, so it means that there is, we can say that there has been an increase in there has been an increase in MR due to the addition of harder and soft phase. Now this MR can also increase when we are dealing with the nanocrystalline nanocrystalline part of it. I mean, when the nanocrystalline form of this. Now, when this nanocrystalline state is achieved, there is something called a degree of coherence. Degree of coherence between the two phases, and especially at the interphase boundary. At the interface. In ferromagnets, where the magnetic dipoles inside this material, they align almost parallelly to the applied magnetic field. When this is the case, the degree of coherence, there is something called an exchange bias. Exchange bias is what when we have a ferromagnet or a magnet or a non-magnetic material, the pins, the poles, dipoles, are pinned or restricted at the point boundary. This is also called the phase boundary, and this gives rise to a wider coercivity and more remonstrance. And there is an exchange coupling taking place in the case of ferromagnet. So, although, however, the magnetic lines of, the dipoles are aligned, there is an exchange coupling, and these dipoles are they represent a certain region called the domain region, or the domain where the electric dipoles are equal. Now, exchange coupling allows the crystallographically and isotropic material to exhibit reminiscence, while approaching those are achieved after full alignment. Now, okay, so there is an exchange coupling in ferromagnets. Now, this process of exchange coupling, what it does, it allows crystallographic as isotropic materials to exhibit reminiscence as well. So once those are crystallographically isotropic, you can find the reminiscence in them as well, and they represent they are equal to those values which have undergone full alignment. Now we will consider a case where we are dealing with an Fe rich composite. Iron rich composite like Fe19, Fe90, neodymium 7, and B3. Now, this compound results in a mixture of hard and a soft phase. So there is a hard phase and the hard phase is Fe14, Nd2, B, this is the hard phase, and the soft phase is nothing but the Fe phase. This is the soft phase and this is the hard phase. We do have a combination of these two phases inside these materials. Now, due to a combination of these materials, what happens is that the magnetic induction, it has been found to increase. Now, these two-phase ferromagnetic alloy, we'll call it two-phase ferromagnetic alloy. When we say ferromagnetic, it means that there is an exchange coupling taking place with dipoles. So it's a two-phase ferromagnetic alloy, and it can be prepared by different means, like it can be prepared by melt spinning, and then mechanical alloying, and also sputter deposition if it has to be deposited in the form of a film atomistically. Now, magnets made up of nanocrystalline materials like yttrium, samanium, and cobalt. They possess uh, an unusual magnetic property due to their extremely large surface area. So we know that in a nanocrystalline material or in nanomaterial, the surface to volume ratio increase. That means the surface is more compared to its bulk than bulk counterpart. Now, one of the magnets, yttrium, samanium, and cobalt, due to the large surface area, they have some unique properties, magnetic properties. And it can be, now if you look at the usual magnet, that is samarium and cobalt, this is the usual magnet, a hard magnet, and if we could make a composite out of this, that means if we could make and if we could add iron or iron and cobalt combined, then the magnetic properties will be similar to that obtained in the case of a nanocrystalline material. Now these are considered to be soft magnets, iron and iron cobalt, while this one is considered to be a hard magnet. Okay. Now when these sort of formation, nanocomposite formation formed, they look something like the one given here. This is how it looks like. Now, typical applications of these high power rare earth metals. So we are using some rare earth metals here. Applications there are few applications of these, like quieter submarines. Quieter submarines. Then automobile alternators. Then the land-based power generators. And motors and ships. Motors used in ships. And ultra-sensitive analytical instrument, like in MRI imaging, these materials are used.